Final. All right, so let's look at the challenge problem when we talk about solubility products. So the solubility, again, is just a equilibrium, but it's an equilibrium where those things that are slightly soluble. So those things that we referred to earlier in the semester or in 111 as being insoluble, right? Only they don't really dissolve. They don't really dissolve because their solubility is very, very small, right? And we can define that as by looking at their KSP as being values that are much less than 1, which means that the majority of the substance is going to remain as the undissolved solid, right? So if we look at this compound here, we have MX, which is a solid. If we tried to dissolve it in water, right, the water is just going to be there to help dissolve it. What 2 ions are we going to get? Well, we don't have really any information here, but what we do have is if we look up in these 2 areas, it will allow us to determine what the charge of the metal is and what the charge of the anion is, right? So the metal, because we have, it's bound to 2 chlorines, each of the chlorines is a -1, that must be a 2+. So this is going to be a 2+ ion when it dissolves. And again, the same with the anion, this X, because it's bound or reacting or combined with 2 sodiums, it's got to be a 2-. So this is the equilibrium that we are looking at, right? And we know that because this is a solid, the K value for this equilibrium expression is going to be the concentration of M2+ times the concentration of X2-, right? Where we're ignoring the product or reactant, excuse me, because that is a solid, right? The only things that are involved are the aqueous, right? We call this a KSP because it's the solubility, how well this is being dissolved. If we looked at the equilibrium values for either one of these, that is going to be referred to as what? This is the solubility or molar solubility. Right? It's the concentration of the smallest whole number concentration of ions dissolved in the solution. Right? That's going to be referred to as, because this has units of molarity, that's what we refer to as molar solubility. The solubility is that we convert this molar solubility to grams per milliliter, assuming the mass is the solid, right? So we're going to convert the molar from moles per liter to grams per milliliter, assuming that the mass that we're talking about is related to the whole mass that's dissolved, right? So we're going to use this mass here, the molar mass of that substance, when we calculate solubility. So you need to distinguish between those. When we talk about molar solubility, that's this mole value. The solubility is in terms of grams per liter, right? Because we care, that's the only reason explanation I can have for it. The book and Alex is going to change the approach here from using an X, which we've done before, to using a different variable, which we call S, right? So they're going to label this as S, right? I think that's dumb because that makes it sound like it's a different process. So I use X all the time because it's still the same process. So if we wanted to calculate this molar solubility, which is what the question is asking us for, right? We're going to ignore all of those because it's a pure solid. Initially, these are both going to be 0, The change is going to still lie towards the reactants because we have to have something. So this is going to be a plus X. So at the end, we're going to have X and X, right? So our KSP is going to be equal to X squared, which is equal to the molar solubility they give us, 1.27 times 10 to the negative 36 is equal to X squared. So X squared, or X, excuse me, I can do that math by skipping a step, is going to be equal to 1.27 times, oh, can't read my own, 1.13 times 10 to the negative 18th mole, right? Which we can all agree 10 to the negative 18th is a really small number. So the amount of this that dissolves is going to be really, really small, right? And because it's really, really small, we're going to say that this isn't, for all intents and purposes, an insoluble compound, right? So when we talked about those insoluble compounds before, that's because the solubility of them is very, very, very small, although there still is one, and this is how we would calculate it. So that was part A, if we have pure water. Right? For number 2, now we have some initial concentration of MCl2. So we still have Mx as a solid is in equilibrium with water of X. Oh, you can't write. M2 plus aqueous plus X2 minus aqueous. Right? We can set it up the very same way. Right, we're going to ignore this, but now we have some initial concentration of the this concentration. So this concentration, instead of being 0, is going to be 0.25. This is still going to be 0, right? Because at equilibrium we want both of them still, we're still going to transition or shift to the product side. So we're going to add X here, add X there. So at equilibrium, we would end up with these values, right? But before, when there was only water, we were seeing that we are only going to dissolve 1.13 times 10 to the negative 18th molar. Right? So that's what X was, this constant. So we can assume that that value is going to be in that same neighborhood, right? It's probably actually going to be less because it's going to reduce the amount that wants to dissolve, right? So the maximum that we could have would be this number. Is probably going to be sometimes less, which means that when we add that to 0.25, what are we going to get? We're still going to get 0.25. So it's safe to assume that X is much, much less than 0.25, so that we, in our K expression then, is 1.27 times 10 to the negative 36. We can approximate this as 0.25 times X, right? Which makes X now 3.175 times 10 to the negative 37th molar, right? If we wanted to check this, we could, right? I'm not even gonna bother it because it's what, 36 orders of magnitude difference. So that's going to be like 30 per 10 to the 30 zeros in front of the number as far as a percent goes. So that's going to be really small, right? So when you look at the book, or when you're looking through some of the explanation, Alex, it's, you know, a lot of the times jump to these expressions here, right? Based on the ions up here. Suggest, again, it's only a suggestion, that you don't try to do that, right? Still set up the ice table, because the ice table will always work, right? And I still set up the ice tables, and I've been doing this for God knows how long, right? So if I think it's a good idea, you should do it too. Right? And the approach for the last one, number 3, would be the same. We would just change this, right? So if we looked at number 3, now our initial concentration here would be 0, and here would be 0.20. We would still be going in this direction. Right? Again, we can assume X is much less than 0.2. So our KFE then is going to be 1 times 3, or 1.27 negative 36 is equal to 0.20 times X. So X here would be 2.54 times 10 to the negative 37th molar. Right. So again, really, really small values. And because we're only calculating the molar solubility, we're going to stop there at that molarity. Whatever the single value of X is going to be our molarity. Just like before, though, if we had not a 1-to-1 ratio of these, if we come back to this initial equation, right, if this was no longer if this was no longer a 1-to-1 ratio, just like before, whatever value we have up here would have to be brought down there, right? And we would have to account for that when we imported or inputted that into our K expression. So the same rules apply. We just have to follow it through, which is where the book or the Alex is going to make those shortcuts, right? It's going to, a lot of the times it's going to skip the step of forming the ice table, which may or may not be confusing. Questions or comments about that? Any questions?